In this video, we're going to be doing a second example problem using Bernoulli's equation. In essence, Bernoulli's equation says that this quantity here is a constant, this quantity being the pressure plus density times free fall acceleration times the vertical coordinate plus 1/2 the density times the square of the speed. So all of that together is a constant as you follow along the flow. When we apply Bernoulli's equation, generally what we do is we evaluate this quantity at two different points in the flow and then equate those different expressions to each other. Another equation we're going to be using to solve this problem is the equation for the mass flow rate. The mass flow rate gives the rate at which fluid mass flows through a particular cross-section of a pipe. So if you have a pipe of cross-sectional area A, the fluid density is rho, and the fluid is flowing along at speed v, then the rate at which the fluid flows through that particular cross-section is given by density times cross-sectional area times flow speed. And then finally, we have the continuity equation. The continuity equation describes how the flow speed changes when the pipe gets either wider or narrower. So let's say that we have a constriction in the pipe where the cross-sectional area changes from A1 to A2. In that case, the flow speed will change from V1 to V2, and all of these quantities are related together by A1 V1 equals A2 V2. So now we're going to put all of this to work in this example problem here. The setting for this problem is a campground. I drew a tent here to make the point that this is happening in a campground. And over here, we have a pipe that the campers use to fill their water bottles. So up here, we have a spigot where the campers turn on the flow. And when the campers turn on the flow, water comes out of the pipe. We're going to say that the diameter of the pipe where the water exits is D1. However, that pipe up here is connected to an underground pipe with a different diameter, D2. We have that the diameters are D1 equals 1 centimeter and D2 equals 2 centimeters. The idea here is that the pressure in the underground pipe must be sufficient so that when the water exits the spigot over here, the campers are able to fill a 1-liter bottle in a 10-second time interval. So the first thing we want to figure out here is how fast does the fluid have to be exiting from the spigot in order to fill a 1-liter bottle in 10 seconds. So I've given you 3 equations to work with here. And for this first part of the problem, you really only need one of these. So see if you can figure out which of these equations you need, and then maybe pause the video and try and solve for that V1 on your own. After you've given that a shot, you can rejoin the video. We're going to solve for that exit speed V1 using the mass flow rate. So I'll start by writing delta M over delta T equals rho AV. As far as the left side of the equation, we can think of delta M as the mass of the water needed to fill the 1-liter bottle, and then delta T would be that time needed to fill the bottle, namely 10 seconds. We're going to solve part A using the equation for the mass flow rate. That is delta M over delta T equals density times cross-sectional area times flow speed. Now, delta M for this process is going to be the mass of water that fills the 1-liter bottle, and then delta T will just be the time it takes to fill that bottle, which was given as 10 seconds. Okay, so what would be the mass of water in a 1-liter bottle? Well, that would just be the density of water multiplied by the volume. The volume is given by that 1 liter. I'm going to go back and put that over here. So let's take this expression for the mass and put it into here. We then have density times volume over delta T equals density times area times flow speed. Notice capital V for volume, lowercase v for flow speed. We can cancel the densities between the two sides. Now, notice that the flow speed we're talking about is the flow speed at the spigot. In other words, I'm talking here about flow speed V1. So I'll put the 1 subscript there. Now, solving for V1, I have V1 equals the volume of the bottle divided by the area of the pipe right here at the exit, and then divided by the time it takes to fill the bottle. What would be the cross-sectional area of the pipe right here at the exit? Well, let's express the area in terms of the diameter. So that would be pi over 4 times diameter 1 squared, and then times delta T. So now let's make our substitutions. So we have V1 equals the volume. So the volume is 1 liter. 1 liter is equal to 1,000 cubic centimeters. In the denominator, we have pi over 4, diameter 1 centimeter, and squared. Delta T was 10 seconds. So the flow speed at the exit must be, put everything in your calculator, I got 127. And as far as the unit checking, notice we have centimeters cubed over centimeters squared. That would give us centimeters, and then down here seconds. So the flow speed at the exit would be 127 centimeters per second. This second part of the problem is sort of asking for the pressure in the underground part of the pipe. However, that pressure is going to turn out to be very close to atmospheric pressure. So what we're going to find instead is the difference between the pressure in that underground part of the pipe and atmospheric pressure. So we're actually solving for that difference rather than the pressure itself. Notice that the quantities related to this underground part of the pipe have the 2 subscripts, V2, D2, and the quantities related to this upper part of the pipe have 1 subscripts, D1, V1. So let me just take Bernoulli's equation over here as written, connecting point 2 in the flow to point 1. I'm going to just copy this over, and then we're going to talk about how we apply this to the problem at hand. So now I've taken Bernoulli's equation and just copied it over here. The first thing I want to do is look at P1 here. P1 would be the pressure as the fluid exits over here at the spigot. However, right here where the fluid exits the spigot, it is in direct contact with the atmosphere. And because of that, the pressure here right at the exit would just be atmospheric pressure. So I'm going to write that pressure 1 equals atmospheric pressure. And I'm actually going to go back to Bernoulli's equation here and just make that one change in Bernoulli's equation. Now remember that the problem was actually asking us to find the pressure in the underground pipe minus the atmospheric pressure. So notice I can rearrange Bernoulli's equation here to get that combination of pressure in the underground pipe minus the atmospheric pressure. So all I have to do is take that P atmosphere and subtract it over to the right side, and then take those quantities that are on the right side now and subtract them over to the left. So we'll just do that rearrangement. And as I do that rearrangement, I'm going to group the like terms. So combining the 2 terms with the y's, I get over here on the left, rho g times quantity, y1 minus y2. I can also combine the 2 terms with the velocities. So I get over here on the left, plus 1/2 rho, and then v1 squared minus v2 squared. And then, as promised, subtracting P atmosphere over to the right, I get on the right pressure 2 minus P atmosphere. All right, now what are y1 and y2? Well, those are undefined because I don't actually have a y-axis in my problem. So maybe I should go back to the setup and stick in the y-axis. Now, as I was about to go back here and put in my y-axis, I realized that I did not set up the problem correctly. I meant to tell you that there was a 1 meter vertical distance between the underground pipe and the spigot here where the water comes out. So I apologize that I left that out. Anyways, let's put in the y-axis. Now we can put our origin anywhere we like. So I'm going to put the origin of the y-axis down here at the level of the underground pipe. So this will be where y is equal to 0. Anyways, now that I set up the y-axis, you can see that we're going to be able to read off y1 and y2 when we need them. Y2 is the level of that lower part of the pipe. Now that lower part of the pipe is level with the origin, so y2 is going to be 0. Now that upper part of the pipe is 1 meter above the level of the origin. So when we come over to the y-axis here, we're going to see that the y-coordinate for this upper part of the pipe is 1 meter. In other words, we now have everything we need to evaluate this first term on the left. Now, what about that second term on the left? In that second term on the left, we have, again, the density, but that's the density of water. We can look that up. Then we have V1, that's known over here, but we also need V2. In other words, we need to know what is the speed at which the water is flowing through that underground pipe there. So I'm just going to copy the continuity equation over here. So I then have A1 V1 equals A2 V2. So V2 would be A1 V1 over A2. Now, A1 would be the cross-sectional area of region 1 in the pipe here. Now, we can express that in terms of the diameter, pi over 4 times diameter 1 squared, and then times V1. A2, that refers to the cross-sectional area of this lower part of the pipe, which is pi over 4 times diameter 2 squared. So cancel the pi over 4s. We then have V2 equals, I'm going to write this as D1 over D2 quantity squared. So 1 centimeter over 2 centimeters. And quantity squared and multiplied by V1, 127 centimeters per second equals 31.8 centimeters per second. Now let's put everything together. I'm going to start by just reversing sides. So I have pressure 2 minus pressure atmosphere equals. Okay, let's evaluate this first term. We have the density of water, which is 1,000 kilograms per cubic meter. Little g, 9.8 meters per second squared. And then y1 minus y2. So coming over here to the figure, y1 would be 1 meter, y2 would be 0, so the difference is 1 meter. Now, to that, let's add the second term. So we have plus 1/2, again, density of water, so 1,000 kilograms per cubic meter. And then we have V1 squared minus V2 squared. I showed you earlier that V1 is 127 centimeters per second, but here I'm doing everything in MKS. So I'm going to convert that to 1.27 meters per second, then squared, minus V2 is 31.8 centimeters per second. I'm going to convert this to meters per second as well, so rounding off a bit, I have 0.32 meters per second. That's squared as well. Putting everything into my calculator, I get as the numerical value 1.06 times 10 to the 4, and I'm going to leave it as an exercise to check that the unit here comes out to be newtons per square meter. but newtons per square meter is also pascals. So coming back to the original figure, the pressure at the exit is the same as atmospheric pressure, but then going down to the underground section of the pipe, the pressure down here would be 1.06 times 10 to the 4 pascals greater than atmospheric pressure. So now we have solved a second example problem using Bernoulli's equation.